Okay, so before continuing, let's look at these two expressions. This is the more correct expression for the potential energy of an object that is of a mass, let's say right over here. This is the correct expression. Under certain approximations, that is, if this special case holds, that is, if we are very close to the surface of the Earth, in that case, this expression is approximately equal to this one, or the potential energy is approximately equal to this one. Now, of course, if you increase the height, then eventually this approximation will no longer be true. Now, if this approximation is no longer true, then you cannot use this expression for the potential energy. So this is the more correct one. Now, another thing, let's just assume that, just a question for you. Let's assume that at this instant, the sun just becomes a black hole. I mean, the sun will never become a black hole, but let's just hypothesize that sun becomes a black hole. Now, what will happen to the gravitational force acting on Earth? Will it increase, decrease, or nothing will change? Who thinks that it increases? Now, this is the question. At this instant, the sun becomes a black hole for an unknown reason. It conserves its mass, it conserves its position, but at that position, we just find a black hole. Now, what will happen to the gravitational force that the sun exerts on Earth? Will it increase, stay the same, or decrease? So who thinks that it will increase? The sun just became a black hole, so it should who thinks it will increase? Anybody else? Who thinks it will decrease? Who thinks it will stay the same? Okay, so that's basically the correct answer. You see, if you look at the expression for the gravitational force, it depends only on the masses and the distance from the centers. It doesn't depend on anything else. It doesn't depend on the density of the object, for example. So whether the sun is a black hole or not, it doesn't have any effect because its mass is the same, its center is at the same, so the distance between the center of the Earth and the sun is the same. Yes?
For sun to become a black hole, its mass should be much larger.
No, we are assuming that for an unknown reason the sun just becomes a black hole with the same mass. So the mass is just constant. So this is one thing that you see in some science fiction movies. So you have this the starship, that is spaceship that is going out, trying to go away from a sun, a star. The star just becomes suddenly a black hole, and there's a stronger attraction towards the black hole. So and the ship just finds it hard to run away from the black hole. This is not science. It never happens. If the sun would become a black hole now with the same mass, its gravitational attraction does not change. But something does change. It has to be very, very, I mean, the mass should be at least, if I'm not wrong, 1.4 times the mass of the sun. 1.4. Not that much, but still it has to be a lot heavier. You see, we had considered the gravitational force exerted by a sphere on an object that is at a distance r from the center. And if you remember, this was the expression we had. Inside the object, the gravitational force just increases linearly, and just outside, it decreases as 1 over r squared. R is the radius of star. So one thing, the gravitational force never goes to infinity, because the gravitational force is created, the net force that an object feels is only due to the mass that is in a sphere whose radius is equal to the distance from the star and your test mass. If you are inside the planet, there is smaller mass that gives a non-zero contribution to the gravitational force, And hence you have this, as you are going closer and closer to the center of the planet or the star, that's why the gravitational force decreases. Now what happens if you... Yes. At the center, there is no gravitational force. Right at the center, it doesn't exist. It's zero. But it's at the center only. Well, this tells me that it's not possible. Of course, as long as we are assuming that the all mass is uniformly distributed. If it's not uniformly distributed, in that case, this expression will no longer be valid, and then you can create another region, another point in which there will be zero gravitational force.
Other lecture, you mentioned about Einstein's correction on gravity. This assumes there is no correction.
There is no such correction. Now, there is one thing. If an object gets smaller, keeping its mass, so what actually increases is this one. You see, this one eventually diverges. So if this radius, keeping the mass same, if this radius gets smaller, on the surface, you will feel larger and larger gravitational pull. This is what happens on the surface of black holes or on the event horizon. The black hole just doesn't become a stronger attractor if you are over here. Whether the star is a black hole or a normal star has absolutely no effect on the gravitational force that you will feel. But if you are on the surface, and if you stay on the surface or close to the surface as the star is shrinking, if you stay on the surface, the gravitational force on the surface gets smaller and smaller. It gets larger and larger, sorry. No, this is just a planet. But eventually it becomes an event horizon, and inside the horizon we don't know what happens. Okay, let's look at one more thing. The escape velocity. Well, we had already done something. We had looked at, if you just take a chalk and throw it up, so what will be the maximum height it will reach? Now it's over there. We can calculate it using the conservation of energy. So 1 over 2 v initial squared should be equal to 1 over 2 v final squared plus mgh, and v final at the maximum height is 0. So h max is equal to m's, we can also cancel, vi squared over 2g. Okay, this will be the maximum height that the object will reach. This is, of course, assumes that we are still very close to the surface of the Earth. And if you increase the initial velocity, it will go to higher and higher heights. Now, if that height gets quite far away, compared to the distances of the radius of the Earth or even further away, then we cannot really use this expression. What we have to do is, okay, this will be the initial velocity, initial kinetic energy. Let's add the potential energy. This is the gravitational potential energy on the surface of the Earth. This should be equal to 0. Eventually it will stop. Plus, or minus g and large M over R max. If we just throw it straight up, eventually its speed will be 0, and this will be the maximum distance that it will reach. Well, the faster we throw it, Gn or R max, this is how we can determine R max. This is equal to large M over R minus 1 over 2 M VI squared. So let's see, if we start from VI very small, very small initial speeds, this term will be very small compared to this one, so R max and R will be comparable. If we keep increasing this initial speed, well, this term will increase and increase, so a positive number minus a positive number, the resulting number will get smaller and smaller. Well, if this gets smaller and smaller, it means our max increases and increases and increases. Eventually, this number will become 0 when when this 1 over 2 MVI squared is equal to Gn M over R. This will tell me that our max will be infinite because this side will be 0. And if 1 over R max is 0, it just means that our max is infinitely large. This is what we call the escape velocity. These m's we can also cancel. 2Gn M over R, square root of. So this basically tells us that if you can throw something with this speed, it will eventually reach infinite distances from the surface of the planet. M is the surface of Earth, R is the radius of Earth. So if you throw an object with this speed initially, independent of its direction, by the way, if you can manage to throw it with this speed, it will reach the maximum distance, the infinite distance. So that's why we call it the escape velocity. If it goes faster than this one, it can of course still reach the infinite distance, but when it reaches the infinite distance, it will have some non-zero kinetic energy also. So this is of course, this escape velocity is you just throw it with that speed and you don't exert any other force. Now this is not actually how the rockets work. In the rockets we keep burning fuel so that it can go further and further. But if you just want to throw a stone that would, let's say, hit the next galaxy from Earth, this should be the speed. Well, it's several tens of kilometers per second, so it's not easy to achieve that speed with a stone. But this is what we call the escape velocity. This is the escape velocity from Earth if you put the mass of the Earth and the radius of the Earth.
Imagine there are two objects holding in space. One is a very large object, like the large mass. The other one is a very small object. And they are very, very distant apart. So, is there...
So this is a large object, this is a very small object.
And the distance between them is huge.
Okay.
And these are the only things in space. So this is the only thing that our system has. Is there a kind of limit to the amount that R can get for the acceleration of that object to zero, or is it be always accelerating to zero?
Well, let's see. Now, if you remember, we were discussing, are we sure that the gravitational force is always 1 over r squared? We don't know if it is really 1 over r squared for distances lower than 0.1 millimeter. We haven't tested it, we cannot compare it with anything. At large distances, we also don't know. Now, one possible explanation for this, the rotation curves of galaxies. Okay, one explanation is maybe it's dark matter, it's an unknown kind of matter that we cannot see. Another explanation is maybe it's just 1 over r squared law is no longer valid. Another one is maybe F is not equal to ma over there. Nobody went to the edge of a galaxy to test whether F is equal to ma. We don't know. Well, the size of the universe, by the way, seems to be finite.
Are there equal Einstein gravity field and normal gravity field?
Yeah, we don't have that distinction. There seems to be only one of them. And Einstein theory seems to be the correct one. Okay, let's come to the Einstein theory. Now we had derived the expression for G from the expression of the potential energy. But we could have also said something else. Let's see, mass times the acceleration of an object. Let's just talk about the magnitudes. If there are two masses exerting gravitational force on each other, this should be equal to G and M times M over R squared. And then we can say that, okay, the acceleration of this mass will be, we can cancel the M's, and A will be equal to G and M over R squared. Now let's see if there's any problem in this calculation, in this treatment. So what is this M over here, over there? Where did we first meet that M? Newton's second law. That's the law of inertia. This is a parameter basically that determines the inertia of an object. It determines how much an object resists to changes in its velocity. What is this mass over here? Well, this is the mass that feels or that creates gravity. Now, in fact, this mass over here is what we call the inertial mass. And this mass over here is what we call the gravitational mass. So basically, they play completely different roles. One is the resistance to force, the other one is the source of the force. Then the question is, why should these two masses be equal? They turn out to be equal, but why are they equal? We don't know. I mean, we are still doing experiments trying to measure any differences between these two masses. But as far as our current measurements tell us, these two masses seems to be exactly equal. That is what we call the equivalence principle. The inertial mass and the gravitational mass, they are exactly equal. Okay, any questions on this one? Or take your time so that this will settle. This idea of two different masses. One is the inertial mass, one is the gravitational mass, and they just turn out to be exactly equal to each other. No.
Why did they not be? Why did they not?
We don't know. But there's one thing we know. If they are not equal, you can forget about Einstein's theory of relativity. General theory of relativity is based on the equality of these two masses. If someday we can prove that these two masses are, if we measure that these two masses are slightly different, then we will know that Einstein's theory of general relativity is false. But for the time being, there is no such deviation between these two masses. So what will be the consequences of these equalities? Now, when we were discussing motion with zero acceleration, motion with constant velocity, we were talking about the relative velocities, and in fact, talking about a velocity without specifying which reference frame you are referring to, we said that it doesn't make any sense. So velocity is always relative to a reference frame, and there is no preferred reference frame, as long as it's an inertial reference frame. No measurement that you do will be able to tell you whether that a given reference frame is in motion or not. Still, we could tell whether a reference frame is accelerating or not. We could isolate an object. So if we isolate an object and if it is accelerating, then that would tell us that that reference frame is not an inertial reference frame, and hence it is accelerating relative to an inertial reference frame. So we could always talk about acceleration, but without referring to any reference frame, but we could never talk about the velocity without referring to a reference frame. So what Einstein says that it is basically because of this one, you cannot even say whether a reference frame is accelerating or not. So essentially you can say that Einstein is contradicting the Newton's first law, because Newton's first law specifies an inertial reference frame, and it tells you how you can determine an inertial reference frame. Einstein says that no, you cannot make this definition. This definition just doesn't make sense. You cannot determine whether a reference frame is inertial or not. And his argument is this. So now you are sitting in this classroom. You are believing that we are fixed on the surface of the Earth, and hence, as long as we can approximate the surface of the Earth as an inertial reference frame, you believe that we are in an inertial reference frame, right? Now the question is, can you distinguish this picture from an alternative picture, which is the Earth had just disappeared after you had entered into this classroom. There is no Earth left. We are in a balloon, air balloon, so that we can breathe, which is accelerating in that direction with an acceleration 9.8 meters per second squared. So here we have these two pictures, which will explain our observations in this classroom. One is, okay, we are still on the surface of the Earth, which is an inertial reference frame. The second one, no, the Earth doesn't exist anymore, or we are not on the surface of the Earth anymore. We are accelerating in that direction with an acceleration of 9.8 meters per second squared. And hence, we are not an inertial reference frame. We cannot distinguish these two descriptions by only doing experiments in this classroom. We have to go out and see if Earth is over there. We cannot distinguish these two because of this equality. On one hand, if the whole classroom is accelerating with 9.8 meters per second squared in the upward direction, we will feel this force that doesn't really exist, which will be m times a. On the other hand, if the Earth is over there, we will be feeling this force, not this one. So if these two masses are identically equal, the forces that we will feel in each one of these descriptions, they will also be identical. And if all the forces are identical, in that case, these two descriptions are completely identical, and there's no way we can distinguish these two descriptions. So let's see some of the consequences of this equality. This equality basically tells us that gravity and accelerated reference frames are basically the same thing. So some of you were asking, can we cancel gravity? Sure. Just jump up from a high building. There won't be any gravity for you. Just imagine you are in a closed elevator, cut the cord of the elevator. When you look around you, no experiment can tell you whether there is gravity and you are falling down or there is no gravity. Of course, until you hit the surface hit the ground. It will be a short experiment, but nevertheless, gravity will be cancelled. Or can you create gravity? Sure, just make sure that you are again in this closed room so that you cannot look outside. You are choosing your reference frame and you want to specify everything relative to that reference frame. And for an outside observer, start accelerating with 9.8 meters per second squared in one direction, so you will feel gravity. And no experiment that you can do in your closed box will tell you that it is not gravity. All the experiments that you do will tell you that you are feeling a gravitational force. This is also another expression of this equivalence principle. So how many of you watched the movie Interstellar? Okay, a good proportion. If you remember in the movie, they built this spaceship which was rotating. So if it's a rotating spaceship, it means if you are fixed on this spaceship, on this rotating part, well, that's an accelerating reference frame. But an accelerating reference frame is equivalent to an inertial reference frame which has gravity. So that way they could create gravity. Now let's go back to our short experiment with the elevator. But this time let's assume that it's in empty space. It's not falling on Earth. It's an empty space. We are looking at it. We claim to be the inertial observer. And this elevator is accelerating upward with some acceleration. And let's assume that in this elevator there's a laser beam. So this is our laser. So what we will see is that, well, the light of this laser will just go straight. Once it leaves the laser, so it will just go on a straight line. This will be the trajectory of the laser light. But of course, as the light goes to the other end of the elevator, well, the elevator will move upwards. So when the laser light reaches the other end, the elevator would be here. Because for the laser it took some time to go to the other end. In that time the elevator just went up because of its acceleration. And so this laser light will hit this point, which is basically on the elevator. In the initial case, it corresponds to some point over here. This is the point A. The point A is a fixed point on the elevator. So this is for the outside observer. Now for the person inside the elevator, you're inside the elevator, this is the laser beam, this is the point A. Now for the outside observer sees that the elevator is accelerating upward. But the inside observer, for him, he's just in a gravitational field. There's gravity. So there's a gravitational acceleration. And the equivalence principle tells me that gravitational acceleration and an accelerating reference frame, they are equivalent to each other. That's also equivalence principle, the equality of these 2 points of view. But of course, the laser will still hit the point A. It will not hit this point, it will hit the point A. Well, let me also name that B point B. Point B is somewhere over here. This is my point B. The laser light will still hit the point A, not the point B. So this will be the trajectory of the laser light. So we have these 2 descriptions which have to be equivalent: an accelerating reference frame or a reference frame under the influence of gravity. So if the equivalence principle is correct, this equivalence between these 2 points of view tells me that light ray has to be bent by gravity. So this is the bending of gravity, bending of light by gravity. This we experimentally observe. Well, of course, light doesn't have a mass. So if Newton's theory of gravity was correct, the light shouldn't have been bent by gravity. But what Einstein says is that it's not the mass that is creating gravity, it's the energy that is creating gravity. So anything that has energy and momentum will create a gravitational force and will be influenced by the gravitational force. So that's why light is also influenced by the gravitational force, according to Einstein, because it has energy, it has momentum, so it will be influenced by gravitational force. Furthermore, it will create a gravitational force also. It will be very small, but nevertheless it will be there. Now let's come to this always said, okay, the geometry, the space-time is bent. Okay, that is what the general theory tells us. Okay, first of all, what is a straight line? So what is a straight line? Shortest length. Again, what is length? Okay, we said that okay, what is length? How do you measure distance? Remember we discussed how do we measure distance in the first lecture, in the first week. Not the first lecture, but first week.
You can drive it to motion.
It's motion of what? You see, what we had, our definition of the length was using light. So it's just we say that 1 meter is the length that light travels in such and such seconds. So it's essentially, starting from this definition of the length, you will see that the light goes on a straight line. That is basically the only physical definition we can give to a straight line. It is the trajectory of a light path. This is a straight line in the physical sense. This is as you said, this is the shortest distance between this point and this point if there is gravity. And this is what is meant by the space-time is bent. You see, it doesn't look like this straight line, right? So it is bent. But this is the shortest distance between this point and this point under the influence of gravity. So this is what is meant by the bending of space-time.
Ya da bizim asansörün içindeki gözlem çerçevesinden de uzay zamanının mutlak olmasından dolayı diyemez miyiz?
Well, what do you mean by the absolute space-time?
Uzay zaman her zaman mutlak değil mi hocam?
What do you mean by absolute? Tell me a measurement. Define things in terms of measurable quantities.
Dünyanın etrafındaki uzay zaman uzay büküldüğü zaman zaman da ona göre bükülür hocam. Demek ki uzay zaman her zaman mutlak ve iç içe.
Okay, make a definition that can be measurable. Okay, this is the bending. I can measure how much it is bent. I can talk about the curvature of space-time. That is something measurable. But what do you mean by absolute? Well, space is relative. Time is relative.
İşte ama uzay zaman relatif.
Space-time it exists. Nobody is doubting that. That's, if you say it's absolute, it means that it exists, fine. But there are people who are doubting whether it exists or not. But let's forget them. In that sense, it's absolute. But what do you mean by absolute? What will be increased? It's speed. Well, you see, if you want to talk about the speed, you have to first choose one reference frame. Which reference frame? There is a?
Your speed will increase.
No, not necessarily. Well, you see, for example, let's talk about some realities. So you are running towards me accelerating. Okay? So initially, your speed is, okay, so let's say you are running in that direction with an acceleration in this direction. Your speed will decrease according to me. Eventually, of course, even according to me, your speed will start increasing. But let's say you are running towards me, I'm also running as fast as you are. This is another description of the same phenomena, and your speed need not increase. Or it might increase.
Did you watch the last week one rocket?
No. Well, you see, whenever you are talking about velocities, you are always referring to some reference frame. And when you are talking about the rockets, etc., you are almost always referring to Earth as your reference frame. Okay, that's fine, but you are choosing one reference frame and you have a description of reality according to that reference frame. But nature, the physical laws should be independent of which reference frames you choose.
You are working a laser world.
Okay.
Now we are trying the vapor, the light space, as a straight line.
Okay.
But from this explanation, we know that it's actually curved.
Well, you see, the problem comes from what do you mean by curved, what do you mean by straight?
We are defining the wave, the light source, as a straight line.
Well, that's a straight line.
We are
Yes.
defining it as a but when we make a measurement, it's not a straight line.
No, when you make a measurement, it will still be a straight line.
What I'm asking that we are defining it as a straight line.
Well, that is as straight a line you can have as possible. There is no straighter line that you can measure or create.
We are defining it.
Well, the line is a mathematical construct. So as your friend said, it's the shortest distance between 2 points. That is, let's say, the line.
We are measuring a straightness of a rod.
You are?
Straightness of a rod.
How do you define that? You shine some laser light through it, parallel to that?
How can we? How can
How? Well, that is, it's the light. That is how we define the straight. So the straight rod will be parallel to this laser light. So this is as straight as you get. You cannot say that it's curved.
That's what I'm asking. We are defining it as a straight.
Okay?
That's
You see, the analogy to you, for example, why do we call it a curved space-time? Take a sphere. Maybe we are just living on the sphere. The straight line from this point to this point will not be this one. It will be this one. This is the shortest line from this point to that point. That's also another reason why we say that space-time is curved. Because it behaves more like this one.
So, what I've noticed in the elevator example that was accelerated was that the observer inside sees the light as bent. So, therefore, it must have, mathematically, you should be able to express it in terms of some polynomial degree greater than 1.
It's a parabola. It's a constant acceleration.
So, can we define a line in mathematics that has a degree less than or equal to 1?
Well, you see, even if you want to, so what you are saying is, let's measure the trajectory, okay? Let's measure the points making this trajectory. How do you measure the trajectory? You measure some distances. You measure the distances along lines. So what is that line?
I'm lost.
No, you are not lost. That's all there is to know. So the line, the straightest you have is the laser line. And since, well, you see, we are also kind of cheating in this example, by the way. We said that, okay, let's say this observer is in an inertial reference frame, this other one is accelerating upward, etc. But the same thing, this whole thing, we can just imagine it as if, well, there's a gravitational force acting on all of them. There's a gravitational force acting on everything, and this observer is accelerating downward. It should be exactly the same description. And there's no experiment that neither this observer nor this observer can do without looking outside, which will be able to distinguish these descriptions. Whether actually everything is under a gravitational field and this observer is falling down, or this observer is the inertial observer fixed and this observer is moving, accelerating upward. No experiment can distinguish these descriptions.
Still, as I said, but to me, it seems like the point that the laser is right, and for there is smaller distance that I can draw, which is
You see, smaller distance, first you have to measure the distance of what you are drawing. How do you measure the distance? Again, back to this problem. Okay, any last questions?
You said that we use the light waves to find the length, so the light always has a speed.
Yes? So in fact, that is why we are using light to define the length, because it will be the same for any observer.
Let's say that I'm moving in this direction at a very high speed. I have a flashlight. I light the flashlight in that direction. Light speed is still constant.
True. So let's say that you are moving in this direction with 99.9999999. You can add as many nines as you like, percent of the speed of light. And you shine some laser light. But when I look at you, what I will see after, let's say, 1 second, your separation, the front of the light and where you are, they are separated by, let's say, 1 millimeter after some time. After, let's say, 1 second, the distances that you have covered will differ by just 1 millimeter. But according to you, this light will cover a distance 299, etc. meters relative to you. So this is basically the relativity of the distance. In your reference frame and in my reference frame, distances will be different. And hence distance is not absolute. We cannot talk about the absolute distance between two objects. And hence, whether you measure the speed of light, or I measure the speed of the light of the torch, we will measure exactly the same number. Although you are moving in the direction of the light with the speed 99.9999% of the speed of light. You see, in this semester, when we were discussing relativity of velocities, etc., addition of velocities, we always assume that what you measure as an observer that is moving relative to me, and what I measure as the distance between two objects should be the same. That was an assumption we made. But the observation just says that assumption doesn't hold. That's a wrong assumption, actually, if you are moving very fast. So we will be measuring different distances for the same objects. Okay, so that's then for this year. Have a happy New Year and see you on Tuesday.